In this video, I want to explore a little bit more deeply something that we've discussed a little bit, that we've hinted at, which is this idea of magnification, okay? And it turns out that there is a magnification factor within the lens's mathematics. And we call that magnification factor just M, all right? And it's really just the ratio of the image height to the object height, right? So in other words, if M is equal to 2, the image is going to be twice as high or as tall or twice as long as the object will be. Okay, if M is 3.5, then the height of the image is going to be 3.5 times the height of the object, right? Many of you have seen this in terms of microscope eyepieces or objective lenses, right? It'll be like 1000x, which means it'll seem as though 1000 times larger than the original image was, or the original object was. As we saw in the last video, another way to simply do this is just to say that that ratio is equal to di over do. Okay, and yeah, there's not really much more to it than that. So if we just want to take a look at one example of what this might look like. Imagine magnifying a beetle. It says a classic magnifying glass has a focal length of 25 centimeters. Let's suppose you take a look at a beetle located 5 centimeters from the glass. Where will be the image located? Okay, so we know we solve that using our classic 1 over do, thin lens equation, plus 1 over di equals 1 over f. Okay, it tells us that our focal length in this case is 25 centimeters. So we know that that is a converging lens because that's positive, right? And we want to know, we also know that the beetle is located 5 centimeters from the magnifying glass, and we want to find out the image location, okay? Now, if I do this, if I put this in my calculator, I get an image location of negative 6.25 centimeters. Okay? What does that negative tell us? The negative is the sign convention that tells us this is going to be a virtual image and that it's actually going to be on the left side. That means magnification. Is it magnified? Well, the original object was 5 centimeters away from the lens, and this is 6.25 centimeters from the lens. So if I do my magnification factor, which that's what part B is asking for. So part B is saying, well, what is M? Well, remember, it is just the ratio of the image height to the object height, which is also just the ratio of the distance of the image over the distance of the object. The distance of the image is 6.25 in this case. Okay, and the distance of the object is 5 centimeters. I divide those by each other, and I just get an M factor of 1.25, right? So in other words, if I'm looking at any object in this magnifying glass, it's going to appear to be 1.25 times larger. In other words, 25% larger than the original object, okay? Now, if the original beetle was 1.2 centimeters long, how long would the magnified image appear? Okay, so for this, we can just go back to the ratio, right? So the magnifying factor is just equal to the height of the image over the height of the object. But really, this works for any dimension. It's stretching any dimension the same amount. So if we want to talk about lengths, then it'll just be the length of the image over the length of the object. Same thing. And we know that that's equal to 1.25. Sorry, that should be an L. This should be 1.25, right? So what is the length of the original object? 1.2. So I have Li over 1.2 centimeters equals 1.25, right? All I got to do is multiply these, and I get a length of an image of being about 1.5 centimeters. Cool, huh? All right. So the bottom line is once you know the magnification factor, okay, you can find out what is the new length, the new height of any object that you look at in a magnifying glass. Okay, you could, you know, turn this into problems involving telescopes and microscope eyepieces. The sky's the limit. Okay, it gets a lot more complicated when you look at telescopes and eyepieces and microscopes because they're compound lenses. It means there's more than one lens to actually create those much more magnified images than a magnifying glass can. But the ultimate idea is still the same. Okay. All right, we're going to do another misconception question. It's the physics of the projector. Remember, projectors are real images that are projected upon a screen. The photographic slide is to the left of a lens. The lens projects an image of the slide onto the wall 6 meters to the right of the slide. The image is 80 times the size of the slide. How far is the slide from the lens? Okay, so we already know from this problem that the M factor, the magnification factor, is 80. Okay. We also know that this M factor is the image distance divided by the object distance, right? Now it tells us that the object, well, it says that the lens projects an image of the slide onto the wall 6 meters to the right. So that's the image distance, right? So the image distance must be 6 meters, right? So how far is the slide from the lens? Well, that's the object distance. So in other words, if I have a little slide here, right, and then I have my lens, right, and I'm ultimately projecting this onto the wall, right, I want to find out what my object distance is. So I know this, right? I know that this is 6 meters, right? And I know that this is 80 times the size of whatever's on here. Okay. So if I want to find out this distance, in other words, my DO, I just use the magnification formula to solve for DO, right? So in any case, this is just going to be DO equals 6 meters over 80, right? We should expect it to be much smaller, and it's going to be. And so 6 divided by 80 is 0.075 meters. In other words, 7.5 centimeters. So if you want to project a little slide 6 meters away from a screen and make it 80 times as big, then it must be only 7.5 centimeters away from the little lens inside the projector. Okay? Most of us at some point have used a projector, whether it's in a classroom or a little home projector situation. And we very rarely ask ourselves, how does this work? Why do I get the image on the wall that I do? Why is it the size that it is? Why does it have to be a specific length away from the projector in order to focus the image? This is the physics and the mathematics that explains that. And that's the fun part of physics. I'll say once again, these little things that we took for granted in our lives now take on a little bit more richness because we kind of understand how they work. All right, part B. Is the image erect or inverted? Well, remember, this is a real image, and real images are always inverted. So B must be inverted. What is the focal length of the lens? Well, just got to use this again, our little thin lens equation. We can find the focal length. Our object distance is 0.075. Our image distance is, 6 meters? And we want to find that focal length. Okay? If I do that, I get a focal length of 0.074 meters, which is equal to 7.4 centimeters. All right? And lastly, is that lens converging or diverging? Well, again, it's a real image, and diverging lenses do not create real images. So it must be a converging lens. Another way to prove that to ourselves is looking, this is a positive number, we got a positive f. Positive focal lengths are all converging lenses. Do you see how it all fits together now? I hope so. I hope it's all clear. Another type of problem where there's many, many, many different examples out there, but really this whole physics of lenses comes down to two main equations. This thin lens equation, which gives you everything you need. The only tricky part is making sure your signs are right. And then this magnification equation, which tells us, how big will our images be relative to the objects that we start with. Okay? With that said, I am going to end this video.